Okay, so let's talk about memory allocation in the kernel. Um, Start reading with pages. Pages! The kernel treats physical pages as the basic unit of memory management. Although the processor's smallest addressable unit is a byte or a word, the memory management unit, or MMU, is the hardware that manages memory and performs virtual to physical address translations, typically deals in pages. Okay, so as programmers, we think in bytes, right? Addresses. So in this case, um, how we think of it as, so we'll do programmers, as if we were to look at memory, we tend to always like look at it in this type of way where we have slots and then we fill things up here, right? But in terms of computer, like MMU, OS, etc., they think in terms of, well, that's ugly. They think in terms of pages, so groups, right, of chunks of addresses in here. And usually, for 32-bit systems, one page, usually, it's configurable, but is 4 kilobytes, so about 4,096 addresses, 64-bit, one page is 8 kilobytes. So 8,192 bytes. Okay. So the MMU is literally like a component in your CPU that actually translates any like virtual address that is from like a user space to the real physical address. So separate from the CPU. Okay. So, therefore, the MMU maintains the system's page tables with page size granularity. So, MMU sees things in pages. In terms of virtual memory, pages are the smallest unit that matters. As you can see in Chapter 19, Portability, each architecture defines its own page size. Many architectures even support multiple page sizes. Most 32-bit architectures have 4 kilobyte pages, whereas most 64-bit architectures have 8 kilobyte pages. This implies that on a machine with 4 kilobyte pages and 1 gigabyte of memory, physical memory is divided into 262,144 distinct pages. So how do we get that? Well, think about it in terms of math. If we just kind of do 1 gigabyte, okay, how many bytes is that? So that's like what's that? 1,024 megabytes, and then 1,024 megabytes is going to be 1,024. Actually, let's just do it. One gigabyte to bytes. Oops. I think it's called GIB to bytes. Come on, I need a better one. Come on, one. There we go. It's this thing here. So we have. Can we just paste it like this? No, we can't. So we have. What the heck? So we have this much, right? And then we'll divide that by 4,096. We'll get this many pages right here. So that's how the math is done. So this is 1 gigabyte in terms of bytes, and this is a 4 kilobyte page in bytes. So the kernel represents every physical page on the system with a struct page structure. So pages are represented as a struct, just like everything else in the kernel. The structure is defined in Linux /mmtypes.h. I've simplified the definition removing two confusing unions that do not help color our discussion of the basics. Okay, so basically, he's kind of minimized the structure declaration so that we don't get confused. But yeah, let's see. So we have along with flags, to atomic T with count map count. We have private. I have no clue what that is. Address space mapping, probably some mapping of the virtual to the physical address, or maybe that's this one right here. And it looks like there's like an LRU cache represented as a linked list. We'll see. Yeah. So let's look at the two important fields. The flags field, okay, the flags field right here stores the status of the page. Such flags include whether the page is dirty or whether it is locked in memory. So if this page is dirty, you can find that in this flag here. Bit flags represent the various values, so at least 32 different flags are simultaneously available. 32 different flags because it is a 32-bit integer. Okay. The flag values are defined in Linux/pageflags.h. So yeah, let's see actually what type of flags there are available. So if we were to go to the source code and go to pageflags.h, so okay, right there, we can see probably all of them right here. So we see dirty, right? That's here. Okay, so this is the 0th, 1, 2, 3, 4th flag. 5, 6, 7. So we have an active one here too, and we even have like a reserved one. Okay, so yeah, looks like there's quite a bit. I think all of them are used. It looks like so. Yep, that's where it's at. So pageflags.h. Okay. So the count field stores the usage count of the page. That is how many references there are to this page. What does that mean exactly? So the count field here is an atomic T, so it has to be synchronized correctly. But references, okay, so how many references there are to the page? That means, I guess, how many, how many virtual address references? So how many things are using the virtual address within that page? Okay. So when this count reaches -1, no one is using the page and it becomes available for use in a new allocation. Okay. Kernel code should not check this field directly, but instead use the function page count, which takes a page structure as its sole parameter. Although internally count is -1 when the page is free. Okay, so if the count is -1, it means that it's no longer in use. So I think we just keep the structure around and kind of reuse it if necessary. Page count returns 0 to indicate free, and positive non-zero integer when the page is in use. A page may be used by the page cache, in which case the mapping field points to the address space object associated with this page. So I think address space is yeah, again, it's a different struct. Okay, so what is a page cache? Maybe that is the mapping given some sort of virtual address, we get to point to the exact page entry in this case. So I think that's from TLB maybe. Guessing. As private data pointed at by private, whereas mapping in the process's page table. So here, I'm curious about this part right here, virtual. So the virtual field is the page's virtual address. So it's the virtual address associated with this page here. Okay, so remember like the page table. So we have a page table, right? Pretend this is a page table. So page table. So these here. Okay, oops. These are page entries. Okay, and these are page entries addresses, right? But what you need is you need a virtual address, and you need to actually go into the page entry. So you need to know which address to go into here to then find the physical address. I believe inside each page entry you'll be able to find, like, make some sort of physical address, I guess, inference from it. So in order to do that, the page entry also needs to have an association with the virtual address. So okay. So the virtual field is the page's virtual address. Normally this is simply the address of the page in virtual memory. Some memory, called high memory, is not permanently mapped in the kernel's address space. In that case, this field is null and the page must be dynamically mapped if needed. We discuss high memory shortly. Yeah, I don't know what that means. The important point to understand is that the page structure is associated with physical pages, not virtual pages. Okay, so this struct page, okay, struct page type, okay, is for physical. Let's remember that for myself. Physical addresses, or physical, what is it? Physical pages. Sorry, physical pages. Okay, not virtual pages. Okay, so this one here, oops, we tie it together. So these represent physical pages. So that's why we need to have that virtual address association. Okay, makes sense now. Okay, therefore, what the structure describes is transient at best. The structure. So, okay, so what this page structure describes is not about getting the data. It's about understanding the association of the physical page, or the description of the physical page. Even if the data contained in the page continues to exist, it might not always be associated with the same page structure because of swapping and so on. The kernel uses this data structure to describe the associated physical page. So it's kind of like metadata. The data structure's goal is to describe physical memory, not the data contained in them. Okay, so that's an important point. The data structure's goal, so this page structure, this struct page here, the struct page here, is to describe physical memory. It's basically to let us know some information about physical memory, not the data contained in them or therein. So we don't really care about the data because the data is going to change anyway, but the physical memory characteristics are what we are interested in. So the kernel uses this data structure to keep track of all the pages in the system, because the kernel needs to know whether a page is free, that is, if the page is not allocated. If a page is not free, the kernel needs to know who owns the page. Okay, so if a page is not free, the kernel needs to know who is the owner. Okay, so who's the possible owner? Possible owners include user space processes, dynamically allocated kernel data, static kernel code, the page cache, and so on. Still not really quite clear on this, but let's move. Developers are often surprised that an instance of this structure is allocated for each physical page in the system. So this struct here, this struct exists for all pages in the system. So remember, we had, like, let's say a gig of memory. If we had 4 kilobyte pages, we have 262,144 of these things here, because that's what represents a single page, and we have this many pages, 262,144 different pages. That's a lot. Okay. So they think, what a lot of memory wasted. Well, let's look at just how bad or good the space consumption is from all these pages. Assume struct page consumes 40 bytes of memory. The system has 8 kilobyte physical pages, and the system has 4 gigabytes of physical memory. In that case, there are about 524,288 pages and page structures on the system. So remember, we have this many pages, 524,288. That means we have the corresponding page structures with them. So they're one-to-one. The page structure consumes then 20 megabytes. So if you have 4 gigs of memory, it's really only going to, 4 gigs of physical memory, it's really only, to represent all your pages, it's really only going to be 20 megabytes. So that's not that bad. Perhaps a surprisingly large number in absolute terms, but only a small fraction of a percent relative to the system's 4 gigabyte. Not too high a cost for managing all of the system's physical pages. Yeah, so in relation to the amount of memory that this represents, this can describe 4 gigs of memory. It's really not that much. Okay. Zones. Because of hardware limitations, the kernel cannot treat all pages as identical. Some pages, because of their physical address and memory, cannot be used for certain tasks. Because of this limitation, the kernel divides pages into different zones. The kernel uses the zones to group pages of similar properties. In particular, Linux has to deal with 2 shortcomings of hardware with respect to memory addressing. So two limitations of hardware. So first, some hardware devices can perform DMA or direct memory access to only certain memory addresses. Okay, so some hardware can only tap in directly to RAM memory to only specific addresses. Okay, and some architectures can physically addressing larger amounts of memory than. Okay, so some architectures can physically address larger amounts of memories than they can virtually address. I think this is a typo here. But yeah, so you can address lots more memory physically than virtually, which is really bizarre. Consequently, some memory is not permanently mapped into the kernel's address space. Okay. Because of these constraints, Linux has 4 primary memory zones. So in Linux, I guess in 32-bit land, I'm going to assume this is 32-bit land, Zone DMA. This zone contains pages that can undergo DMA. There's Zone DMA 32. Like DMA, direct memory access for hardware to tap into memory directly, this zone contains pages that can undergo DMA. Unlike Zone DMA, these pages are accessible only by 32-bit devices. So anything that's like PCI or PCIe. On some architectures, this zone is a larger subset of memory. Okay, so this is bigger than DMA in terms of the addresses. This one, I'm guessing DMA works for both 16-bit and 32-bit devices, so ISA and PCI. This one's probably just PCI. Zone normal. This zone contains normal, regularly mapped pages. Okay, and then zone high mem. This zone contains high memory, which are pages not permanently mapped into the kernel's address space. These zones and 2 other less notable ones are defined in linux/mmzone.h. The actual use and layout of the memory zones is architecture dependent. For example, some architectures have no problem performing DMA into any memory address. Okay, so for some CPU architectures, there's no address like range or limit in which it can perform DMA. So basically copy data directly to memory or read data directly from memory. So it could put stuff, like hardware could just dump stuff into memory directly. That's what DMA is. Yeah. Let me double check. Okay, direct memory access. Okay, so direct memory access is a feature of computer systems that allow certain hardware subsystems to access main system memory independently of the central processing unit, so CPU. So it doesn't need to go through the CPU to access main memory. So I don't think you need to do like interrupts and things like that. So let's just read this. Without DMA, when the CPU is using programmed input-output, it is typically fully occupied for the entire duration of the read or write operation, and is thus unavailable to perform other work. With DMA, the CPU first initiates the transfer, and then it does other operations while the transfer is in progress, and it finally receives an interrupt from the DMA controller when the operation is done. Oh, okay, so the CPU doesn't have to care, like be occupied by the transfer. So it probably helps the hardware initiate the transfer, but the rest is just like going on with the hardware, with the CPU not supervising it. Okay, so this feature is useful at any time that the CPU cannot keep up with the rate of data transfer, or when the CPU needs to perform work while waiting for the relatively slow I/O data transfer. So it doesn't have to like supervise. Cool. All right. Okay, so in those architectures, zone DMA is empty and zone normal is used for allocations regardless of their use. As a counterexample, on the x86 architecture, ISA devices cannot perform DMA into a full 32-bit address space because ISA are 16 bits. Because ISA devices can only access the first 16 megabytes of physical memory. Okay, sure. Consequently, zone DMA on x86 consists of all memory in the range from 0 to 16 megabytes. So the first 16 million addresses is reserved for DMA. Okay, and zone high mem works in the same regard. What an architecture can and cannot directly map varies. On 32-bit x86 systems, zone high mem is all memory above the physical 896 megabyte mark. On other architectures, zone high mem is empty because all memory is directly mapped, and I think that's called zone normal. So the memory contained in zone high mem is called high memory. The rest of the system's memory is called low memory. Okay, so zone normal tends to be whatever is left after the previous two zones claim their requisite shares. On x86, for example, zone normal is all physical memory from 16 megabytes to 896 megabytes. On other, more fortunate architectures, zone normal is all available memory. So table 12.1 is a listing of each zone and its consumed pages on x86 32-bit. So one thing to know is that I think the kernel on 32-bit x86 can only access, or it's only 1 gigabyte of reserved physical memory. So although this zone high mem looks like it's a lot, it's probably not. It just goes up to the 1 gig limit. So anything 896 and above, up to that 1 gig is called zone high mem. And then everything else in between here is zone normal, and then zone DMA is reserved for the first 16 million addresses, or 16 megs and below. Okay, so Linux partitions the system's pages into zones to have a pooling in place to satisfy allocations as needed. For example, having a zone DMA pool gives the kernel the capability to satisfy memory allocations needed for DMA. If such memory is needed, the kernel can simply pull the required number of pages from zone DMA. Okay, so it's not a hard and set rule. It seems like if the kernel really needs more memory, it can just like start getting stuff from other regions. So note that the zones do not have any physical relevance, but are simply logical groupings. Yep, so it's just groupings in code used by the kernel to keep track of pages. Although some allocations may require pages from a particular zone, other allocations may pull from multiple zones. For example, although an allocation for DMA-able memory must originate from zone DMA, a normal allocation can come from zone DMA or zone normal, but not both. Allocations cannot cross zone boundaries. The kernel prefers to satisfy normal allocations from the normal zone, of course, to save the pages in zone DMA for allocations that need it. Okay, so let's read this again. So the kernel prefers to satisfy normal allocations from the normal zone, okay, of course, to save the pages in zone DMA for allocations that need it. So although we can cross boundaries and things like that, kernel still has preferences, which is why these logical groupings still make sense. For any like allocations necessary for the kernel, it will try to satisfy from zone normal first, because zone DMA needs to be reserved for like those hardware devices that may need to do the memory transfers. Okay, so yeah, but if push comes to shove, say if memory should get low, the kernel can dip its fingers in whatever zone is available and suitable. So not all architectures define all zones. For example, a 64-bit architecture such as Intel's x86-64 can fully map and handle 64 bits of memory. Thus, x86-64 has no zone high mem, and all physical memory is contained within zone DMA and zone normal. So in 64-bit systems, we don't have such a concept of the next 896 and above as zone high mem. Okay? We only have these two, where zone normal is the rest of all physical memory. Okay, so here's a zone struct. Each zone is represented by struct zone, which is defined in Linux mmzone.h. So I don't know what watermark is, probably some limit, low mem reserve, page set, which I guess has specific number of CPUs. Like each CPU has an associated page set lock to do stuff. Okay, free area, another spin lock, two spin locks. One is for LRU, one is for general, it seems like. Okay, pages stand, flags, wait table, span pages, present pages, associated name with the zone, which I guess is like DMA normal, or is it DMA and then DMA normal, right? Yeah, no, zone normal, zone DMA, and so on. Oh, let's just keep going and take a look. So the structure is big, but only 3 zones are in the system, and thus only 3 of these structures. Okay, cool. So you only have 3 of these things because there's only 3 memory zones. And if it's x86-64, it'll be only 2 memory zones, so 2 of these structures. So let's look at the more important fields. The lock field is a spin lock that protects a structure from concurrent access. Figured that one out. Note that it protects just the structure and not all the pages that reside in the zone. Okay, so it just protects this struct and not the pages inside of that zone, which makes sense. A specific lock does not protect individual pages, although parts of the kernel may lock the data that happens to reside in said pages. The watermark array holds the minimum, low, and high watermarks for the zone. Okay, so basically what is the lowest address, right? The minimum that qualifies, and then the highest address for that zone. So there's 3 things. The kernel uses watermarks to set benchmarks for suitable per zone memory consumption, varying its aggressiveness as the watermarks vary vis-a-vis free memory. The name field, unsurprisingly, is a null-terminated string representing the name of this zone. The kernel initializes this value during boot in mmpagealloc.c, and the 3 zones are given the names DMA, normal, and high mem. So not zone DMA, not zone normal, not zone high mem, just DMA, normal, and high mem. Okay. Getting pages. Now with an understanding of how kernel manages memory via pages, zones, and so on, let's look at the interfaces the kernel implements to enable you to allocate and free memory within the kernel. So the kernel provides one low-level mechanism for requesting memory, so kind of like a malloc kind of thing, but in kernel land, along with several interfaces to access it. All these interfaces allocate memory with page size, granularity, and are declared in linux/gfp.h. The core function is struct page, so you get back a page pointer, struct page pointer, alloc pages, gfp mask, and then an order. Not sure what that is. Let's see. Oh, this allocates 2 to the order. Okay, so 2 to the whatever number of physical pages. Okay, and returns a pointer to the first page's page structure. Okay, so you allocate a group of pages based off of this order. So you can really only allocate like 1, 2, 4, 8, 16, 32, 64 pages and so on at a time. and then you'll get back a struct page, which is going to be the pointer to the first page, page structure. Okay, and then on error returns null. So we look at the GFPT type and GFP mask parameter in the later section. You can convert a given page to its logical address with the function page address. Okay, so this gives you a void pointer. You want to get a page address given this page here. Okay, its logical address would be that page entry address. So this returns a pointer to the logical address where the given physical page currently resides. If you have no need for the actual struct page, you can call unsigned long get free pages. So this is a different way to actually get the free pages. Again, same API-ish, except that what do you get back? You don't get back a page struct. So this function works the same as alloc pages, except that it directly returns the logical address of the first requested page. Okay, so you get back an address number. Because the pages are contiguous, the other pages simply follow from the first. If you only need one page, two functions are implemented as wrappers to save you a bit of typing. Okay, so you want to alloc one page here with alloc page, or you can do it through get free page that returns pretty much, I think, the address. Yeah. So these functions work the same as their brethren, but pass 0 for the order in one page. So wrappers, there's wrappers that will have order equals 0. Okay. So getting 0 pages. If you need the return page filled with zeros, so initialized to just only zeros, the function we can use is unsigned long get 0 page with the GFP mask. Notice how we don't need the order anymore because order is 0 in this case. Or not, sorry. Yeah, wait. Oh yeah, get 0 page. Yeah, get 0 page. Only one page. Yeah, 2 to 0 is 1. Yep. This function works the same as get free page, except that the allocated page is then 0 filled. Every bit of every byte is unset. This is useful for pages given to user space because the random garbage in an allocated page is not so random. It might contain sensitive data. All data must be zeroed or otherwise cleaned before it is returned to user space to ensure system security is not compromised. Table 12.2 is a listing of all the lowest level page allocation methods. So all of these here that we just reviewed. Alloc page, this is one page, get one page. This is get 2 to the order pages. This is like to get the address, the logical address. This is to, or of a single page. This is get logical address of a group of pages. Okay, the order, and then zero out that single page. Get a page and zero everything inside. Okay. So freeing pages. A family of functions enables you to free allocated pages when you no longer need them. First, you have this free pages with a dunder. Then you have free pages. I'm guessing these last two here utilize this one in some way, maybe. And then we have free page, which is going to be only free one single page. Okay, so you must be careful to free only pages you allocate. Passing the wrong struct page or address or the incorrect order number, so order number is like how many, can result in corruption. Remember, the kernel trusts itself, unlike with user space. So the kernel will happily hang itself if you ask. Yeah, it'll do anything because it trusts itself. So it's not going to doubt or deny. So let's look at an example. Here we want to allocate 8 pages. So basically 2 to the 3 here with this get free pages is going to be 8. So we get the unsigned long page, the logical address, called get free pages with GFP kernel flag, and the order of 3 to get that logical address. Okay, and to handle the error, we don't have memory. Sure. Okay, so now page is now the address of the first of the 8 contiguous pages. So we had 8 pages. The return of get free pages is a number, right, that represents the address of the first page. Okay, so and then here's an example to free 8 pages. We'll just free 2 to the 3 pages here, starting from this first page that we got earlier. Okay. So the GFP kernel parameter is an example of a GFP mask flag. It is discussed shortly. Make note of the error checking after the call to get free pages. A kernel allocation can fail, and your code must check for and handle such errors. This might mean unwinding everything you have done thus far. It therefore often makes sense to allocate your memory at the start of the routine to make handling the error easier. Otherwise, by the time you attempt to allocate memory, it may rather be hard to bail out, because you might have done several things to alter the state of the kernel by then, and you don't want to do that necessarily, because then you have to undo it if you have an error to allocate. These low-level page functions are useful when you need page-sized chunks of physically contiguous pages, especially if you need exactly a single page or two. For more general byte-sized allocations, the kernel provides kmalloc. It's kmalloc for general byte size, because before we were doing allocations at the page size. Now we want to do allocations at the byte size. Okay. So we have kmalloc to help us with that. The kmalloc functions operation is similar to that of user space's familiar malloc routine, with the exception of an additional flags parameter. The kmalloc function is a simple interface for obtaining kernel memory in bite-sized chunks. If you need whole pages, so if you want to grab whole pages, the previously discussed interfaces, basically everything here in this table, right, is a better choice. For most kernel allocations, however, kmalloc is the preferable interface. So most of the time we'll use kmalloc. So the function is declared in Linux /slab.h. So void, get a pointer, void pointer back, called kmalloc. This function is called kmalloc. Give size and give flags. Okay. So we don't really need to. Oh, it is kind of like malloc. It's like normal malloc. Provide the size, except that we need the flags parameter, which is what it says. Exception of the additional flags parameter. Okay. So the function returns a pointer to a region of memory that is at least size bytes in length. The region of memory allocated is physically contiguous. On error, it returns null. Kernel allocations always succeed unless an insufficient amount of memory is available. Thus, you must check for null and after all calls to malloc and handle the error appropriately. Okay, that's standard malloc stuff. So let's look at an example. Assume you need to dynamically allocate enough room for a fictional dog structure. Okay, so let's do it. So we want to allocate enough memory to hold a single struct dog and store that pointer in P. So we can just do kmalloc with the size of struct dog and then pass in that GFP kernel flag and then handle the error if we don't get anything back, if P is null. So if the kmalloc call succeeds, P now points to the block of memory that is at least the requested size. In this case, the requested size is going to be the size of this struct dog. The GFP kernel flag specifies the behavior of the memory allocator while trying to obtain the memory to return to the caller of kmalloc. Okay, so what is this flag stuff, right? Let's see what it's all about. This GFP mask flags. So you've seen various examples of allocator flags in both the low-level page allocation functions and kmalloc. Now it's time to discuss these flags in depth. Okay, flags are represented by the GFP type, which is defined in Linux /types.h as an unsigned int. So it's kind of just like an alias in this case. GFP stands for get free pages. Oh, okay, get free pages mask. One of the memory allocation routines we discussed earlier. So this is one of them. Okay. The flags are broken up into 3 categories: action modifiers, zone modifiers, and types. Action modifiers specify how the kernel is supposed to allocate the requested memory, and in certain situations, only certain methods can be employed to allocate memory. Okay. For example, interrupt handlers must instruct the kernel not to sleep because interrupt handlers cannot reschedule. In the course of allocating memory, okay, zone modifiers specify from where to allocate memory. As you saw earlier in this chapter, the kernel divides physical memory into multiple zones, each of which serves a different purpose. Zone modifiers specify from which of each zones to allocate. Typical flags specify a combination of action and zone modifiers as needed by a certain type of memory allocation. Type flags simplify the specification of multiple modifiers. Instead of providing a combination of action and zone modifiers, you can specify just one flag. The GFP kernel is a type flag, which is used for code and process context inside the kernel. Let's look at the flags. So basically telling that this page or whatever is for the kernel. Okay. Yeah, I gotta stop here actually, so we'll continue next time.